the system will stretch more and more. Or simply, in other words, I can say that force is now directly proportional to displacement x. Potential energy can be actually defined in terms of work done. Whatever work I am doing will be stored as potential energy in this particular system. Kinetic energy Ke is equal to half mv square. Generally, the loss in kinetic energy, and that will be equal to product of the masses divided by sum of the masses and multiplied by the initial velocity square. Hey all, I am Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we were dealing with work, energy and power. We dealt with different types of energies and how mechanical energy is actually related to kinetic and potential energy. And we also saw what happens to conservation of mechanical energy. Now, we are going to dive into one small topic, that is elastic potential energy. Just like gravitational potential energy, there exists a quantity that is known as elastic potential energy. So we'll be learning about elastic potential energy, and the final thing we have in this particular chapter is collisions. So let's see that. So what exactly is elastic potential energy? So we do know that there is two different types of potential energies depending upon is it due to its position or is it due to its configuration, basically setup. So we can say that if any object that is having a mass m is kept at a particular height, then we can say that okay, it will have gravitational potential energy stored in that particular object, which is given by the equation U is equal to mgh. Just like that, if there is any object, for example, let's say in a spring or a rubber band or a bow and arrow, then we can say that there exists a potential energy, that is, there exists a type of potential energy possessed by that particular object due to its configuration or simply by its setup. That type of potential energy is known as elastic potential energy. For example, we do know what is the equation for spring constant, that is F is equal to minus Kx. If you don't remember that, I'll show you that also. For example, we know that for a spring, let's say this is a spring. Now, if I say this is a spring which mass m, which is attached at the very end, if I stretch that particular spring, then I have to do work or apply a force. Then the string will be, or spring will be stretched like this, right? It will be stretched like this. Let's say through a distance of x. Through a distance of x, the spring will be stretched. So what am I doing? I am applying a force and there is displacement being occurring. That is, if I consider this to be the mean position, x is equal to 0, then I can say that by applying a force, I am actually moving that particular spring from its mean position, or simply I am just producing displacement. So if I apply more force, more displacement is being produced. So I can just simply say that the more force I apply or give it to the system will stretch more and more. Or simply, in other words, I can say that force is now directly proportional to displacement x. So this particular force is the force I apply. So I am the one who is pulling on that particular spring. So I am the one applying that force. So I can say that the external force applied on that particular system is directly proportional to displacement x. So I can say that okay, this is external force applied. Or in another sense, I can say that the spring, in this particular case, the spring is also applying a force. By Newton's third law, we know that if I apply a force, there will be a pair of forces. That is, one force will be in this direction, one force will be in the opposite direction in the same magnitude or with the same magnitude. So I can say that the spring will be applying a force. Let's call it as Fs. So the force applied by the spring will be in the opposite direction, and that will also be directly proportional to the displacement that is being produced. For example, you can say that if I let go of this particular string after stretching it for some time, if I let it go, it will go back to its initial position, which means where did it gain that energy? Where did it get that particular force? So it is actually stored energy there. We'll discuss that very soon. But again, since it is experiencing a force in the opposite direction, that is why it is going in the opposite direction when I suddenly let go of that particular spring. So that particular force is also directly proportional to displacement. Or we can just say that introducing a spring constant, I can say that Fs, negative Fs will be equal to Kx, where K is the spring constant, which we already learned. So instead of writing any negative signs on the left hand side, we usually write it on the right hand side. So I can convert this equation as F is equal to negative Kx, where F is the spring force. So this is where the equation F is equal to minus Kx actually comes from. And K is the spring constant. X is nothing but displacement. All this we already learned, but I just wanted to refresh your memory. So why did I tell you all that? Why did I take an example of a spring? Again, you all know, because we are dealing with elastic potential energy. So we need something that is elastic. So what better example rather than a spring? So if I say that there is a spring, let's say this is a spring and it is resting right now, a spring which is having mass m attached to it. It is negligible, but the thing is that there is a mass and it is attached to a spring and it is resting like this. So I can say that now the spring is in equilibrium, or simply the mean position of this particular case, in this particular case of the spring, is 0. So there is 0 displacement. I am taking this position, this mean position, as the origin. So from this point, I am referring if the spring is being contracted or elongated, or is it stretched. So what I'm going to do is that I'm going to take this spring and stretch it out. Okay, let's say a distance of x. So I'm going to stretch this particular string through a distance of x in that particular direction so that it is elongated. Then I'm going to see what is the speciality of that particular situation. Why is the spring going back? Is it just because of the force I applied? All that things I'm going to check it out. So what happens? Now I have stretched the spring through a distance of x meters or x units. Now if I let go of this particular spring, we know that this is going to go back to its initial position. Maybe it will oscillate so much, but it will go back to its initial position. So why is that particular spring returning back to its initial position? The reason for that is because somebody is giving an energy so that this can go back to its initial position. Somebody is providing that energy. Who is providing that energy? So very simply, it is me who is providing that energy. Just like we saw before, as I apply a force and produce displacement by stretching that particular string, what happens? I am doing a work. That particular work is now being stored as potential energy in this particular string. Or I can simply say that when this is stretched, due to its configuration, that is, due to its present configuration, this will be having stored potential energy, or rather it will have stored elastic potential energy. So that is why the spring will recoil. That is not recoil, it will actually go back to its initial position when it is suddenly let go of. So again, we'll find mathematically what is the equation for that particular elastic potential energy that is contained within this particular spring. For gravitational potential energy, we found out that it was equal to mgh. Now we are going to find what is elastic potential energy. So I am going to consider a spring with spring constant k. So I am going to consider a spring with spring constant k, and it is being stretched out through a distance of x meters or x units. It is stretched out through a distance of x units. Now, so the only thing I do know is that the force applied, or the spring force, is directly proportional to displacement, or negative Fs is equal to Kx, or rather I can actually say that since Fs is equal to minus Kx, which also means that this is because this is the force applied by the spring. I can also say that external force, that is the force I am applying, is equal to this particular spring force. So I can say that F external will be equal to Kx, because Fs is equal to F external. The only difference is that Fs will be in the opposite direction. So I can say that F external will be equal to Fs negative Fs, or simply F external is equal to Kx. Why I'm doing is this because I want to find out what is the work done by me, or simply what is the work done that is stored as potential energy in this particular system. That is what I'm trying to find out. So the next thing, obviously, I have to find out what is the net work done by the system or work done by me, which is stored in that particular spring, so that I can get an equation for the elastic potential energy. So what is the equation for work done? It is force times displacement. If I'm saying that the force experienced by that particular spring is F external and the displacement produced is X, then I can say that if we take the product of those two, I'll get the net work done. But if I'm saying it generally and I'm assuming that, okay, when it is stretched through a distance of very small displacement dx, then I can see it for a larger distance, or general assumption I can make. Why I am making a general assumption is because when I am pulling this particular string, or when I am pushing this particular spring, what happens is that the force I apply will automatically vary, because when I'm starting to pull this particular spring, it will be one force applied, let's say F1. But as I pull it and stretch it and elongate that particular spring, what happens? The force I apply to pull that particular spring actually varies, which means it is a variable force. So we have already seen what variable force is. So we know how to take the work done for a variable force. It is nothing but integral F dot dx. So you can take any assumption you want that is justifiable for you. So in order to find out the elastic potential energy, what I'm going to do is that I'm going to find out the work done, and that will be equal to integral, since this is a variable force being applied, I have to apply integral sign F external dot dx. Now since both of them are acting in the same direction, that is force is also applied in the same direction, I can say that the angle between those two will be 0 degrees. So even though F dot dx is here, it is F dx cos theta. So cos 0 is nothing but theta is equal to 0. So cos 0 is nothing but 1. So I can just simply write integral F external into dx. So since cos 0 is 1, we can say that F external times dx, when we integrate that, we will get the net work done. And before integrating, we have to know from where to where are we integrating. So we do know that the mean position is indicated by 0, which means we are starting with 0. And where are we ending with? We are ending with x units, which means my lower limit is 0, my upper limit is capital X. So from 0 to x, I am integrating this particular quantity. So then I can simply say that this will be equal to integral 0 to x F external times dx. What is F external? F external is nothing but kx. You just substitute that there, kx times or kx dx. So there is actually integral results you have to understand and by heart. So that particular results will be introduced to you in second PU by your mathematics ma'am. But for now, to solve this particular equation or integration, we have to know one basic result. That is, so integral x dx will be equal to, it's given by the relation x raised to n plus 1 divided by n plus 1. There will be a constant of integration usually, but for us we don't need that. So we'll just stick on to this particular equation or result. So this will be the general assumption. So this result is what we are going to apply here. So again, sir, there is one more quantity, that is k. So again, I told you in the previous classes also, that is, if we are performing integration on a constant quantity, then automatically that constant quantity will come right outside of the integral sign. Here k is a constant, it is the spring constant. So I can say that it is safe to assume we can write this as k into integral 0 to x dx. So again, integral x dx is nothing but x raised to n plus 1 divided by n plus 1. That is, x raised to n is equal to x raised to n plus 1 divided by n plus 1. Or simply we can say that for x, it is x raised to 1. So that means the answer will be k into x raised to 1 plus 1, that is x square divided by 1 plus 1, x square by 2 in the limits 0 to x. So we have to apply the limits also. The way we apply the limits, again I have explained this in detail in the class, but still the way we apply the limits is that we apply the limits upper value minus lower value. In the place of this x, we are going to substitute the upper value, then subtract it from the lower value. That is, we are just trying to find out the average. So it is k into upper value, that is capital X square divided by 2 minus lower value, which is 0 square divided by 2. So 0 by any quantity is 0 itself. So we'll get the final result as k capital X square divided by 2. Or simply we can say that elastic potential energy will be equal to half kx square. We can take the general assumption that elastic potential energy of this particular spring system is equal to half kx square. So that is a very small derivation about elastic potential energy. The only confusion you'll have is during the integration part. With practice, it will actually become more and more easier for you. There is multiple results depending on what type of quantity you are actually integrating. Is it 1 by x? Is it x? Is it log x? Is it e raised to x? So different types of laws are there. You'll actually learn it in your mathematics chapter. For now, this is the only understanding we need to integrate x raised to n. So generally we are saying that x raised to n dx will be equal to x raised to n plus 1 divided by n plus 1. That is the only result you need for now. We'll see further. When we go further, we might need even more results. So in that particular time, we'll discuss that in detail. So again, one particular doubt is that we found out work done, but sir, you are saying that it is energy. How is work and energy related? So again, whatever work I am doing in order to stretch this particular spring is actually now stored as potential energy in that particular system. The more I work, that particular work is being converted as energy and it is stored inside this particular spring. So energy and work are actually related. So we can actually say that potential energy can be actually defined in terms of work done. Whatever work I am doing will be stored as potential energy in this particular system. That is why work and energy are actually related. That is why we found out the work done, because it will be equal to the potential energy of that particular system. That is the elastic potential energy of this particular spring system. And its SI unit is nothing but joules. So since elastic potential energy is out of the question, the next quantity we have to deal with is simply power. So what exactly is power? In terms of physics, we say that power is nothing but the rate at which work is done, or simply power P is equal to W by T. That is work divided by time. That is work per time, or simply it is the rate at which the work is completed. So power can be defined as how quickly a work is being done. Any work, in terms of power, we can say that the rate at which that particular work is done, is completed, that will indicate power. For example, we can say that if a Lamborghini can travel from Mysuru to, let's say, Bangalore in 1 hour, let's say that is the work done by that Lamborghini car, and Alto takes like 5 hours to reach there, then I can say that Lamborghini has completed that work in less amount of time, or in fewer time span, in lesser time span. So I can say that the power of that particular car will be more. It's just an example so that you can understand the concept. The rate at which work is done is defined as power. The rate at which work is done is known as power. And we have the equation, that is W by T, which can also be written down as F dot S divided by T. So that is one more equation. If you want, you can also write it in one more terms, that is F dot S, let's assume that the angle between F and S is 0 degrees. So we can write it as Fs by T. So if I take these two together, then I can say that it is displacement by time. So I can simply say that this will be equal to force times velocity, right? So you can also write it down like that, or simply you can also write it down as F dot V. Both are not wrong, both are correct. So you have multiple equations in order to satisfy what is the method to find out power. So you have multiple equations. One is work by time, one is force dot displacement, or F dot S divided by T, or again you can write it as F dot V. So you have multiple ways in order to find out power. This is general equation. If you go to an electrical circuit, it is completely different. It is this product of voltage and current. So again, it is very different. This is very different. So generally we can say that power is the rate at which a work is done. So you can expect numerical questions from this particular part. So they can give you the force applied, they can give you the displacement produced, and it is done in this particular time. So how much power will be spent? So the SI unit of power, it's very easy. Work, what is the SI unit? So we can say either joules per second as one SI unit. So joules per second is one SI unit, or else you have force Newton, displacement meter, time second. So you can also see it as Newton meter per second. That is one more way of representing its SI unit. So again, you can also use watts. You can because watts is actually the name of a scientist, that is James Watt. So to honor him, we actually use the SI unit of power as watts. So you can also use watts. That is why when you burn a light bulb, we express it in terms of watts, 60 watts, 80 watts. So like that. If you're using an engine or something, we express it in terms of horsepower and all that. So don't worry, the power will be further studied in your second PUC actually. So for now, you have to understand what the definition of power is, how the equations are related, and how different SI units are there. That is enough for power. And the final thing you have to understand is collision. So what exactly is collision? Collision is defined as when two bodies actually comes into contact with each other for a short period of time and there is exchange of energy and momentum taking place, then we can say that it is a collision. So simply, when two bodies meet for a very short period of time and there is exchange of energy and momentum, then we can say that it is known as a collision. So you might have seen car collisions, you might have seen your friend colliding with someone else, you might have seen you colliding with the desk, you might have seen the car colliding with the bike. Many collisions are there in day-to-day life. If you play caroms or billiards, where you snooker, where you place like this and you just do that, all those are very good examples of collision. So here we are going to learn about two different types of collisions. That is, we are going to learn about elastic collision and we are going to learn about inelastic collision. So here we are going to learn about two different types of collisions. One is elastic collision and one is inelastic collision. So what is elastic collision? When collided, it bends or it stretches. Is that elastic? No, it is not elastic. Collisions are actually defined in terms of energy, momentum, and how they are exchanged. So collision usually happens for a very short period of time. So we define them and we quantify them based on the momentum and energy exchange between them. So I can clearly say that for elastic collision is the type of collisions in which kinetic energy and momentum is conserved. So if kinetic energy and momentum is conserved before and after collision, then I can say that those type of collisions are actually known as elastic collisions. Now, what will be inelastic collision? Kinetic energy and momentum are not conserved, so it is inelastic collision. Huh? No, not exactly. So momentum is actually always conserved. In this particular case, we can say that linear momentum. So linear momentum is conserved. So we can say momentum is forever conserved. We can always say that momentum is conserved. So we can say momentum is conserved, but Ke, that is kinetic energy, is not conserved. So the cases in which just momentum is conserved and kinetic energy is not conserved, we assume it to be inelastic collision. So we can just say that elastic collisions are the type of collisions in which momentum and kinetic energy is completely conserved, and inelastic collision is the type of collision in which kinetic energy is not conserved but momentum alone is conserved. So those are the different type of collisions, and there is one special case where there is one subtype of inelastic collision occurs. That particular collision is known as perfectly inelastic collision. So one subtype of this inelastic collision is perfectly inelastic collision. So perfectly inelastic means that this criteria is completely followed. That is, if two objects are moving like this and suddenly there happens a collision, after the collision these two objects together move along. So that is the type of collisions where perfectly inelastic collision happens. So it is a rare instance and I have never seen that, but maybe you're lucky enough to see that. So don't worry, I'll give you examples for what is elastic collision, what is inelastic collision, what is perfectly elastic collision. But for now, understand that elastic collision means kinetic energy and momentum is conserved, but for inelastic collision, momentum is conserved but kinetic energy is not conserved, and there is a subtype that is known as perfectly inelastic collision. So let us take a look at the example of elastic collision. So what exactly is elastic collision? It is where kinetic energy and momentum both are conserved. So when there is a mass, let's say m1, and it is striking or impacting or colliding with mass 2, let's say mass 1 was moving with u1 velocity and mass 2 was moving with v1 velocity. So after the collision, what elastic collision dictates is that both of them should not lose their kinetic energy and they should not lose their momentum. So if I'm saying that, okay, mu was the initial momentum of this particular particle, mu1, and here it is m2v2, and they're having the kinetic energies half m1 u1 square, and here it is half m2 v2 square, like that. Then the net effect should not be vanished. That is, the net kinetic energy and momentum should not have any difference after the collision also. That is, momentum should be equal to this quantity on the right hand side. Here also it should be same, and here also it should be same. That is, here after collision. Here it is after collision. That is, if two objects are striking with each other with immense force, then if it is coming at a particular speed and striking on some object, then after the collision also, the sum of their momentums should be equal, and the sum of their kinetic energies should also be equal to the sum of the kinetic energies after collision and sum of momentums after collision. Both sides should be same. It is very rare, maybe if you go to space you can observe that, but I haven't observed any collisions that is perfectly elastic. It is very rare. I haven't seen any of that. In day-to-day life, it is practically impossible, because if a car hits a bike, the energy is transferred. There is a change in kinetic energy. Momentum is conserved, but there is a change in kinetic energy. So again, since perfectly elastic collisions are not practically possible, we don't look too much into that. But if you're trying to study higher order mechanics, then we can definitely look into that even further. But for now, this is what elastic collision actually means. Inelastic collision, I told you, where kinetic energy is not conserved. That is, sum of momentums before collision should be equal to sum of momentums after collision. That is true. But sum of kinetic energy should not be equal to sum of kinetic energy after collision, because there should be some change. Some energy should be lost in some other form. So if that happens, then we can say that, okay, it is an inelastic collision, that the collisions we actually see in our day-to-day life. And in that particular case, we dealt with one particular subsection, that is perfectly inelastic collision. That is when mass m1 moving with, let's say, u1 velocity incidents or collides with mass 2 moving with v1 velocity, and after the collision, these two will get m1 and m2 will move together as a common body with a new velocity v. That is, this object is now colliding with the second object, and both the object will act as one system, and together they will move like this. You might have seen some funny accidents where a bus will hit the back of a car, and the car and the bus together will move together as one with one common velocity. In that particular case, momentum is conserved, but the kinetic energy will be different. Some form of kinetic energy loss will be there. So in those type of collisions, we can say that it is perfectly inelastic. It is perfectly inelastic. It is a rare case, but yeah, that too happens in our day-to-day life sometimes. You can imagine a carom board or a snooker table as a good example for collisions. Now again, collision happens in all three directions. We do know that, we have seen that, but in this particular case, we will only be dealing with collisions in one dimension, that is along just a straight line. Just one dimensional collisions is the only thing we will be studying. So in order to prove that, I have to show you that, okay, momentum and kinetic energy is conserved. So this will be the equation, or this will be the equation to find out what is the velocity after collision. So we'll find out for elastic collision and inelastic collision. So let's assume a case where, so the question paper makers are asking you to show that relative velocities before and after collision remains the same in a perfectly elastic collision, not inelastic collision, but in a elastic collision. Okay, so we have to show that relative velocities before and after collision is remaining the same. So this is BC and that is AC. So what is BC and AC? It is not before Christ and after Christ. It is simply before collision, and that is simply after collision. So we do know that if this is in elastic collision, then automatically momentums before and after collision should be same. So where we are going to start with that particular concept, that is momentums before collision will be equal to after collision. So P before collision will be equal to P after collision. Okay, so in that particular case, momentum of the first system is momentum of this particular body plus momentum of this particular body. That is m1 u1 plus m2 u2. That is the net momentum before collision. m1 u1 plus m2 u2. The net momentum. Momentum of first body plus momentum of second body should be equal to net momentum after collision. So this should be equal to m1 v1 plus m2 v2. So that is the first assumption that we are going to make. And now I am going to take all the m1 terms to one side and all the m2 terms to one side. That is, all the second quantities in one side, all the first quantities in one side. So then I can say that m1 u1 minus m1 v1 will be equal to m2 v2 minus m2 u2. So again, m1 is common, so I can say that, okay, m1 into u1 minus v1 is equal to m2 into v2 minus u2. So we can write like this, and we can say that, okay, this will be the equation representing momentum before collision and momentum after collision. So let's keep it as equation number 1. Now, similarly, we are going to write an equation in terms of kinetic energy also. Similarly, if we represent kinetic energies, then I can say that, what is the equation for kinetic energy? Half mv square, right? Kinetic energy, Ke, is equal to half mv square generally. So here, initial velocity is u, so I can write half m1 u1 square plus half m2 u2 square will be equal to half m1 v1 square plus half m2 v2 square. Again, same process, we'll just rearrange them and write. So I'm taking half as common, so I can write half here. Then I can write m1 u1 square minus, again same process, if you write it like this and rearrange it, I can say that m1 u1 minus m1 v1. Similarly, m1 u1 minus m1 v1 square will be equal to half into m2 v2 square minus m2 u2 square. We'll get an equation like this. Here again, m1 is common, I'll take it outside, and here m2 is common, I'll take it outside. So if I do that, I'll get the equation as half m1 into u1 square minus v1 square will be equal to half m2 into v2 square minus u2 square. So this is the equation we get. Let's name it as equation number 2. Now what I'm going to do is that I understand that, okay, this equation is fine, but this equation does not look that particularly nice. You can also do it in the next step, but okay, I don't like it right now itself. So what I'm going to do is that I'm going to look at this particular quantity and I'm going to recognize that, okay, this particular quantity is being written down as a square minus b square. So since I'm a very good math student, I know that a square minus b square is nothing but a plus b into a minus b. Understanding that particular concept, I'm going to rewrite this as half m1 into u1 plus v1 into u1 minus v1 will be equal to half m2 into v2 minus u2 into v2 plus u2. So again, this is not with this one, let's keep it aside. So you will get this particular equation. If you want, you can cancel out the half and half from here. So you'll get m1 into u1 plus v1 into u1 minus v1 is equal to m2 into v2 minus u2 into v2 plus u2. That is the equation regarding kinetic energy. Now let's name it as equation number 3. So we already have equation number 1 beforehand, that is in terms of momentum. So if I take equation number 3 and divide it with equation number 1, then I can actually write, okay, let's write the numerator first, m1 into u1 plus v1 into u1 minus v1 on the left hand side, and on the right hand side it will be equal to m2 into v2 minus u2 into v2 plus u2. Okay, all of this is being divided by the first equation, which states that m1 into u1 minus v1 is equal to m2 into v2 minus u2. All the terms which are similar, you are allowed to cancel them. And again, here it is u1 minus v1, u1 minus v1. So u1 minus v1 here, u1 minus v1 here. v2 minus u2 here, v2 minus u2 here. So the only remaining quantities here is that, the only quantities remaining here, it is u1 plus v1 is equal to u2 plus v2. Or simply by rearranging, I can write it as U2 minus U1 is equal to V1 minus V2. This is our proof. That is, difference in initial velocity is equal to difference in final velocity. Right? Difference in initial velocity, U2 minus U1 just means that it is the difference in initial velocities of the two bodies. Now it is being equal to V1 minus V2. That is okay. We'll take the absolute value or we'll take the modulus value. The point is that the difference is indicated and they both are same. So we can say that we have successfully proved for a elastic collision. We can say that relative velocity before collision is actually equal to relative velocity after collision. That is the first proof. And this is a very simple derivation. You only have to cancel out a few terms and then voila, you will get the result. So, the next question or the next problem is to derive a relation between or simply to find out what is the kinetic energy lost in a perfectly inelastic collision. So, for that particular derivation, I am assuming a situation where body 1 is moving with a velocity u1 and body 2, which is having a mass m2, is actually at rest. Now, body 1 is going to collide with m2 and together they are going to move as one single system with a velocity v. For example, you can imagine you are playing carom board and you're keeping a striker and you have just flicked the striker and now the striker strikes a coin and now both of them are heading together in a common direction. So, since we are dealing with one-dimensional motion, obviously we are going to go in one particular direction. If it is at an angle, then cos theta will be involved. Then we have to do more mathematics. You don't want that, right? So, we are saying that, okay, this is in one dimension. And so, this body will be colliding with the second body and together they will be moving with one common velocity. So, again, in that particular case, for an inelastic collision, we do know that momentum is conserved. So, momentum is conserved. It is kinetic energy that is not conserved. Momentum is absolutely conserved. So, we can just say that m1, that is momentum before collision and after collision, will be equal. So, m1 u1 plus m2 into 0 because m2 is in rest, right? If there is no velocity, then momentum will be 0 for that particular mass, will be equal to m1 plus m2 into v, because now this particular mass, that is m1 and m2, are moving together as one single system. So I can say that this will be equal to m1 plus m2 v, or simply I can say that m1 u1 is equal to m1 plus m2 into v, or simply v is equal to m1 u1 divided by m1 plus m2. So we actually have the first equation, that is v is equal to m1 u1 divided by m1 plus m2. So we have devised an equation for velocity. Why? Because we are going to find out what is the loss in kinetic energy, or simply just del Ke, that is the change in kinetic energy. In order to find that, we need an expression in terms of V. That is why we have devised this particular relation. Now, loss in kinetic energy, let's indicate that by delta Ke will be given by, if you want to find out change, it's very simple, right? Final quantity minus initial quantity. But if I do that in this particular situation, I'll get a negative sign. So in order to avoid that particular negative sign, I'm just taking initial value minus final value. That will also give you the change, but the negative sign will be avoided. In physics, in this particular case, negative sign will just indicate that, okay, energy is lost. If you take Kf minus Ki. Everything is right, no other problem is there. The only thing is that you'll get the net output as negative value. That just means that, okay, there is loss in kinetic energy. Kinetic energy is lost, energy is diminished. So that negative sign is indicating diminishing value, or simply something is lost. But in order to avoid that negative sign, because you will all get confused with the negative sign, I'm just taking Ki minus Kf, because again, the magnitude value is not going to change, only the signs are going to change. So in order to avoid any confusion with the negative sign, I'm just going to take Ki minus Kf. So delta Ke just signifies change, Ki minus Kf. Ki means initial kinetic energy. Initial kinetic energy is given by half m1 u1 square plus half m1 u2 square, that is 0, because the second body is obviously at rest, so we don't have to bother about that. This subtracted from minus Kf, the final kinetic energy. So finally mass 1 and mass 2 are moving together, which means m1 plus m2 whole into half m1 plus m2 v square. So this is the change in initial minus final kinetic energy. This will be equal to the loss in kinetic energy delta Ke. So we are going to find out what is that particular value, or what is an equation to find out that particular loss. So again, here we have a V and we have an expression for V. So we can say that this can be written down as half m1 u1 square minus half into m1 plus m2 into, instead of v square, we can actually write m1 u square divided by m1 plus m2 whole square. That is m1 u1 divided by m1 plus m2 whole square. So this can be actually written down as half m1 u1 square minus half m1 plus m2 into m1 square u1 square divided by m1 plus m2 whole square. So again, we can cancel out 1 m1 plus m2 and the numerator 1 m1 plus m2. So that just cancels out. Then we can actually write this equation as, this can be written down as, I'll just take this half as common because that's easier. So I'll just take this half as common, then I can write m1 u1 square minus, there is no m1 plus m2, so the remaining quantity is m1 u1 square divided by m1 plus m2. This will give you the loss in kinetic energy delta K. So this is the equation I have arrived at. It is not completed. We can take m1 u1 square also outside, right? Because there is an m1 u1 square here, there is an m1 square u1 square here also. So I can just take it right outside. So if I take it outside, what will be remaining? Here, if m1 u1 square came outside, there will only be 1. 1 minus, here I am taking 1 m1 and 1 u1 square, which means there will be m1 divided by m1 plus m2. 1 minus m1 by m1 plus m2. So delta Ke will be equal to half m1 u1 square into, then the only remaining quantity here, nothing will be there, minus 1 m1 will be here divided by m1 plus m2 will be here. This will give you, this is u. So this will give you your loss in kinetic energy or change in kinetic energy. And we can simplify this furthermore. There's no harm in doing that. The equation will be much more simplified. So let's do that. Here it will be half m1 u1 square only. Inside we can cross multiply that. Then this will be m1 plus m2 minus m1 divided by m1 plus m2. So again there is a plus m1 and a minus m1. So it will be equal to, this can be rewritten as, half into m1 m2. So m1 m2 divided by m1 plus m2 whole into u1 square. So this will be equal to loss in kinetic energy. So the equation in order to find the loss in kinetic energy is very simply obtained, like a couple of steps, but the actual process is very easy. So you can easily find out what is the loss in kinetic energy, and that will be equal to product of the masses divided by sum of the masses and multiplied by the initial velocity square, and there is a half here. So that will actually give you the loss in kinetic energy. So with that, we have finished our work, energy and power chapter. So again, it is a very interesting chapter, but from an examination point of view, only this much is important. It is very important that you study this particular chapter. So I'll see you on very soon with a new and long chapter, that is system of particles and rotational motion. So until then, thank you.